like TV from other dimensions has a somewhat looser feel to it.
Yeah, it's got an almost improvisational tone.
Hey, what's up, Elizabeth? How is everyone doing? It is office hours time. Happy test day. How's everyone doing? What questions are there? Hair just keeps getting longer. What questions are there? Good to see you here, Elizabeth. It is test day. I was replying to emails in the background. It is test day. What questions are there? Whatever people want to review. We are pushing back the My Pearson assignments. Been trying to get My Pearson to do its My Pearson thing, and it's like, nope. Up. We can do that for these. Okay, so I can change it for one class right now. One class is getting changed right now as we speak. One class is getting changed. One class. There we go. One class is getting changed. Nope. I was wrong. Well, that loaded quickly. So that loaded quickly, which is good. So is My Pearson working officially now? My Pearson, what are you doing? Let's see what class is saying. I'll worry about changing that here in a little bit. Sorry, can you explain parameter of interest? Influence Phat gave me integer 0, not sure what it means. Send me that HTT. You're on Discord, right? Send me your code on Discord. Send me your code on Discord, and I'll take a look. If you can send me your code on Discord, HTT, and let's talk about parameter of interest. Let's go over here. So send me the code, and I will take a look. Let's go over here and talk about parameter of interest. So key terms we have right now are going to be things like population, sample frame, sample, and parameter of interest. You know what? Let's go here. Okay. Hey, what's up, Mubarak? Good to see you here. So, and yeah, if you have questions, let me know. Ask all the questions. The population is going to be every person or thing we want to understand. Can we do some randomness? You bet, Elizabeth. We'll do a randomness right after this. Population is going to be every person or thing we want to understand. The parameter of interest is what do we want to understand about the population. The sample frame is who do we have access to sample? And then the sample is going to be individuals or items we collect data on. So parameter of interest, the only key word right here is parameter, because sometimes people say the population parameter of interest. All they're talking about when they say population parameter of interest, we don't have that underlined, population parameter of interest, the only keyword, struggling to find probability given how many people polled and the percent of support something has. Which one are you working on, Carter? Feel free to let me know. We'll work on that after a randomness problem, Carter. You got it. So if you look at this right here, the parameter is what we want to understand about a population. So let's take a look. Put all the questions. Let's work every question. Thank you so much, everyone, for being here. Let's do it. We go out and sample UTA students by going to pedestrian walk and speaking to 300 students about whether they like Stat 201. Okay. So can you identify the portions of this problem right here, what we have? Let's start coloring it in and see what we have. So what is going to be the population of interest? So the population of interest is going to be what? So every person or thing we want to understand. So what is the population of interest for this problem? So think about, in this problem, who do you want to understand? What people or things do you want to understand? So population, you'd say, well, the group we want to understand. UTK students, great job there, Emma. Excellent work. Color changing pen. Stop doing the color change. So UTK students, we understand UTK students. What is the sample? Which this one's a little bit easier. The sample is going to be what? We're doing the easy ones first right here. The sample would be what? Like be very specific. So we have the definitions up there to help us. We're talking about this. The sample is going to be what? So what would the sample be right here? And then we'll do a randomness, and I think we'll do Carter's question next. Great job. So the sample is going to be what? Are we lagging? Hopefully we're not lagging much. We've been really good as of late. Like we've only had a few like lag spikes and then it's went down and the numbers say we're doing good. The 300 students we speak to, it might have, hopefully it's just because it looks like we're doing a little. Sometimes we can hit a lag spike. I'm so sorry, everybody. We might be good now, but every once in a while there's a little, YouTube does a lag burst on us. Probably sudden link. I pay for gig speed internet. And I wish I had gig speed internet at all times. The sample frame, I think, is where things get confusing. So the sample frame is all people or things we have access to. What is the sample frame right here? What is the sample frame? What is the sample frame going to be? So the sample frame is going to be all people or things we have access to. So can you explain kind of who we could theoretically speak to? So the sample frame doesn't mean we sample all the people in the sample frame. It just means these are people we could have spoken to. Like, anybody around here, like who are the people we could have collected data on? That's what the sample frame is. Like to say like, well, you could speak to these people because these are the people you'd be around, or like these are the items you would have access to. Students on pedestrian walk, exactly, the ped walk students. So it'd be anyone on ped walkways where we have access to them. So the parameter of interest is what we want to understand about them. So when you think about the parameter of interest right here, the parameter of interest, which is, we should just highlight only parameter. Not with red. Stop doing that word. So the parameter, because sometimes you call it the population parameter of interest. Yeah, you could say that's kind of a more broader sense. Emma, you are correct. People who are on campus, walking to campus, and technically people who are around ped walkway. So Emma, you're on the right track right there. Like people who are on campus, walking around campus, and specifically people in this region that we're in. Because think, are we going to speak to everyone who walks by us? This is the sample frame right here. Are we going to speak to everyone who walks by us? No. But we're going to speak to people who are around us. Like, theoretically, we could speak to somebody who is near us. It doesn't mean they will make it in our sample. It's just theoretically, these people were in our sample frame. Like, these are theoretical people you could talk to, the people walking around you. If somebody's not on campus, as Emma's pointing out, great job, Emma, right there. If someone's not on campus, then they're not in the sample frame because you can't speak to them. And then the population parameter of interest, and the only important word there is parameter. Everything else is just icing on the cake. The only thing we need to focus on there is parameter, which is what we want to understand. So what do we want to understand? Probably the proportion of people who like 201. Like we're asking a yes/no categorical question right here. We're saying, do you like 201? And they just say yes or no. So hopefully they say yes. Hopefully they're like, yeah, it's best class ever. I love it. Love statistics. Yeah, I don't know. They're like, it's okay. I like stats. Their opinion on Stat 201 is the parameter of interest, and probably like the proportion of students who like Stat 201 or something like that. Or we could do the average rating of Stat 201 or something like that, because that's what we're interested in measuring about the population. So hopefully that helps out here with the terminology. HDT, did you send me the thing on Discord? I can take a look because I knew you had a question. I think it is. Are you Shadow? I'm too afraid to click it and I'll lose it. I think I know which person you are on Discord. Starts with Shadow. Is that you on Discord, HDT? I'll go grab your code if it is. I'm too afraid to click a message because I can't like unread messages on Discord. I'm so afraid I'm gonna like read someone's message and then forget and be like, oh, I forgot to reply to a person. That's you. Good. Perfect. I'm gonna say hi. Hi. There we go. Okay, let me hop to space. We're here in space. I'm gonna pull up the stuff. Let me take a look. Thank you, HTT, for sending me that. That's why Discord is so awesome right here. Okay, I'm getting everything going. Gonna look at the influence plot. I'm running the code right now. You're getting integer 0? Let me hop back over here. I'll show you. Your code's running. I'm losing my mind. Here we go. Where am I at? All right. I need to set up my thing so it like so I ran your code right here and it looks to be working. What we're getting right here is the influence plot. You should be getting this point right here. Do you see this? 90 minutes for the exam. Good question, JG. 90 minutes. And does this look right here, HGT? You should be getting this right here. This is the influence plot. And you might be getting integer 0 here if you don't have any influential points. But you should have... Run all the code again. You know what it might be? Yeah. Like that. HGT, let's throw some 50 points. Like once you see, you're like, I need to run all my code above. So thank you so much. Do not worry. That's what I like. Like once you see, you're like, I got it. And I think you're getting integer 0 right here, which means what an integer 0 means is It's an integer vector of length 0. So if you do this, you should get integer 0. So I didn't know that for a long time what integer 0 meant, but it means an integer vector of length 0. So if you do something like here as dot character, you can get character 0 because that's a character vector of length 0. It's a blank character vector with no positions in it. My instance plot looked crazy earlier. Yeah, this one's pretty crazy right here. This one's like also, that's like a huge influential point due to huge leverage and a very large deleted studentized residual. So great stuff right there. Excellent work. Help me blank out the screen real quick. I'm going to close down everything here. Don't save. Close out the whole environment. Look at this. Brand new R. It's a brand new world. It's a whole new world, everyone. Look at this. Boom. Whole new R right there. Nothing open. Okay. I know we're about to do randomness probability, but you also have touched on the margin of error afterwards. You bet. You got Emma. Great questions, Emma. Thank you for being here. Let's do some randomness. You know, we can actually do a randomness problem with R right here because we can simulate random numbers. Let's say we want to simulate our friend thinks that they are truly they think they're truly a 50% free throw shooter. Now let's not use 50%, let's use 30%. So we simulate them shooting free throws right here and we see what could happen. So they're going to shoot, let's say 20 free throws, and let's write this down right here. 0 to 2 represents making a free throw. So there's a randomness problem. 3 to 9 represents missing a free throw. Oops. Question 1. According to this simulation, according to the way this simulation was created, what is the probability they make a free throw? So according to the way the simulation was created, what's the probability they make a free throw? Yep, speedrun video for chapter 13. Let me go grab that one for you. I'll throw this in the chat right here so you can see it should be in there. And I think I have a timestamp too. So I tried to timestamp everything in all the speedrun videos. You can hear speedrun music in the background, which I do have all my audio going through here, right? Good. Am I losing my mind? Oh, good. It's one big video. Checking the conditions. I did use it, right? Oh, when our sample's unusual. Truth. Here we go. Found it. Here is the link. And Emma, you are correct. There's the link right there. So we have this right here. And the probability according to this simulation is 2 divided by 10. So it is 20% because we have 2. Oh, wait, 30%. 30%, Emma. Sorry, Emma, this will be 3 numbers. Yeah, great job, Emma, right there. I was like, wait a minute. Because we have the numbers 0, 1, and 2. So 0, 1, comma 2, and that is 3 numbers. So 3 numbers, and this right here would be 7 numbers. So, and you can also think about this, when you think about the way numbers work, so the way numbers work is going to be, when you do 0 through 9, and why do we often do 0 through 9? Well, we want to use 1-digit numbers. So 0 through 9 is just the same as 1 through 10. It's just that we're taking this 0 here and moving it to the other side. So you're really doing like 1 through 9, but then you also have the 0 over here. Like the 0 is the extra number. And it just lets us do 1-digit number combinations by doing 0 through 9. So that's why we often do 0 through 9, because it's like it's 1 through 10, but it's 10 numbers. No, don't worry. Even I was like, wait a minute. Let's throw some 20 points out. Thank you, Emma. Don't worry. Even I was like, wait. It's so easy to make a small mistake like that. And that's what we try to catch before the test. So great job right there. We caught it. And let's go here to sample. We're going to do, 20 free throws. So let's sample the numbers 0 through 9. We're going to sample 20 free throws. And you do not need to know how to do this. This is not in 201. Okay. So let's grab this number line right here and see how many we make. There's our YouTube numbers. We were talking about that during class. We're going to sample this right here. And let's go in here. So what do we notice about this simulation? Wow, this is insanity. This is a crazy simulation right here. So take a moment, and according to the rules of the simulation, let's go grab that. So according to the rules of the simulation, let's go here with question number 2. How many did we make? So how many free throws did we make in the simulation now? How many free throws did we make? Which is absolute insanity. And do remember that 0 through 2 is make. So always have your rules written down so you can access them. 0 through 2 is make. So this represents make right here. And 3 through 9 equals miss. This is insanity. This is what happened. So how many free throws did we make? I'll start showing the answer right here. It's pretty crazy from what I can tell. 8 might be. 1, 2, 3, 4, 5, 6, 7, 8. Great job. Yep. So 8. We made 8 out of 20. I guess that's not that high. That's 40%. So in this simulation, we made 40% of the free throws. So we can still do like x equals 8, n equals 20. So the sample proportion for this is going to be, and that x over n equals p hat. So we can get a sample proportion like what percent of free throws did you make? And it'd be 40%. So the question could be worded like what percent of free throws did you make? Is this making sense right here to everybody that we can find 8 over 20 free throws and say our sample proportion of free throws made is 40%? In this simulation, we made 40% of our free throws. And it's about what the simulation expected. We expected 30% by the way the numbers are coded. So are there these basic questions, all division? It can be stuff like that, Carter, yep. Division questions, figuring out probability questions, things like that, sort of questions like this. I think Carter, did we do Carter's question? Then there was another after. But this is kind of a basic idea of a simulation, understanding the way the simulation is set up, like with the way it is coded, what's the probability, and it's coded in a way that we'd expect 30% right here. So we could actually code the answer into this if we want to see, like, it's not going to show us, but we could go, well, it'll show us after we do it. We could go the probability that a number is greater than or less than or equal to 2. And then we can take the mean of this. And this is what's so great about this. And we get 45%. We won't always get, there's 30%, finally. But if we were to increase the simulation right here, now it's going to be super close. And that's a key thing to know, that if you increase the number of trials, so we're actually able to simulate this inside of R pretty quickly. You're not meant to know how to simulate this, but this is the backbone of what we do when we do simulations by hand right here. On a scale of easy to hard, where does this exam fall? I would say 1 step above exam 1 difficulty. I've been seeing some grades come in for people who have to take it early, and the grades are a little bit lower. Well, the test will tell you how many round, and if you get something wrong that you think you got correct, please let me know. One person already contacted me and actually had to kind of correct a question, and they got the points back, and then I reviewed everyone's exam. It was very early on. They were like the 3rd or 4th person to take the exam, and I reviewed the exam, so please contact me. There is the possibility that something could be like not properly worded on the exam, doesn't make quite sense. Please contact me. We always try to be as fair as possible as we can to all students, but just contact me and be like, hey, Brian. And then the person contacted me, they're like, hey, this doesn't really make sense. And then I fixed it. No, that's fine, Emma. That's what we're here for. This is a conversation. This is the ask questions at any time. So this is your chance to ask any questions. I think, did we answer Carter's question? We try to do as many questions as we can. And that's what so, we're glad to have you here. So ask all the questions you have. Maya was asking about practice tests. Feel free. And then we have Z-score. Carter had a question, though, that we haven't done yet. So Carter said, Brian, I'm struggling to find the probability given how many people polled and the percentage support something has. Carter, what question should we do now? Everyone take a vote or just say what you want done? What do you want to cover? What do you want to talk about? It is open floor right now, as far as I can tell, for questions. We can cover a topic. We can do, if My Pearson's working, we can do a My Pearson problem. It is open floor for questions, open season on questions. All questions will be done. Can you explain number 7, part 1? You bet. Let's see what that looks like. Number 7, part 1. Let's go. And this is on the practice test, right? Number 7, part 1. And I think we have some, yep. That's going to be about, It's going to be over here. Here it is. Okay. Here is number 7. We've got some work on it already. Just ignore the work. Number 7 is about a local grocery store. And they'll do my question next right here. Number 7 is about a local grocery store. And the first part of this question I'll explain before we look at some of the answers here. We're doing a giveaway at this grocery store. Numbers 0 and 1 represent winning. Where numbers, what are the other two numbers? The other 2 through 9 represent losing. So how many numbers total are there that we're simulating from? How many numbers total are there that we're simulating from? How many numbers total are we simulating from right now? So we have 0 and 1 represent winners, and 2 and 9 represent not winning. So how many numbers are we simulating from when we do this right here? We're simulating from how many numbers? How many numbers are we simulating from just by the way this is right here? Just by virtue of these numbers. 10 numbers. Great job, Lurker. So is it Lurka or Lurker? So we're simulating from 10 numbers. 0 through 1 and 2 through 9 are the numbers that are being simulated. We're simulating from 0 through 9, where the numbers 0 and 1 represent winning and the numbers 2 through 9 represent losing. So what is the probability of winning? Well, in this set of numbers right here, there's 2 numbers. So 2 out of the 10 possible numbers. And so the way the question is worded for the first part is based on how they are coded. Based on how the numbers are coded, we'd expect to see 20% winning. This is based on the way the simulation is coded right here. Does that make sense? On basically, Lurka, is it? Lurka, it's fine either way. Whatever you want, I'll say it as long as I think it's fine to say. Like, yeah. Your call. So I can just call you X if you want to. That's whatever you prefer. So we have here these are 2 out of the 10 possible numbers that exist. Does that make more sense, Maya, right there? This is based on the way it's coded. This question right here is asking about the simulation. Then in the simulation, I'll call you X. Cool. But if you asked what % of time do people win, I think there is 23 wins in the simulation, and there's 100 total trials. So the question could say, like, in the simulation, what % of winners were there, which is a question not asked. And then we would say there's 23% winners or 23 winners out of 100. But great questions right there. Keep asking more questions. This is just based on the way the simulation is coded, which is a different question than in the simulation, but based on the way the simulation is coded. Good question right there. And so, yeah, and I'll try to we'll answer all the questions. This is open floor. Ask questions. We'll try to put them in order, and we'll just keep answering questions. This is your call to ask a question. Open a new sheet. There we go. What do we have right here? Any topic you want covered? Any sort of question on my Pearson? We got a call from Julio at the end of class. It was really awesome. He was just giving some positivity right there. And that's just really awesome to see. He's always he's joined many videos and helped out and really been a positive. Just, I don't know. He's really helpful for students. He's just been, I don't know. It's really nice that a lot of Tennessee volunteers still want to help out and see other students succeed and be like, you got this, and stay positive. So that's what we're gonna do. Stay positive. Put on a little music. What questions are there? It is office hours. Chill music. Saw part of the morning office hours and I didn't really get what was going on task 1. Yeah, do you want to go talk about task 1 some more? Yeah. Let me pull up which part of task 1 were you wondering about? It's like I've memorized this song now. I'm very picky about which music I take from YouTube. And we are getting the assignment downloaded. And here's the assignment. And then X, we'll do that next. You got it. Which part were you wondering about? Are we going to get the probability of all? We can do one of those if you want, X. Would you want to do those at least one problem? I can review at least one problem after this. There's some of those on the test. There's definitely at least one problems on the test. And the better you get those. What exactly does the integer value mean, and what is the unusual row? So an unusual, something that has undue influence, Did I write integer value in here somewhere? Are you talking about you were seeing integer value? HTT, are you talking about when you saw integer? Are you talking about? I think it was you asking this earlier. Yep. Yeah, definitely. You got it, X. We'll do one of those next. Are you talking about when you see? Are you talking about that? We don't specifically need to know what this means. This is integer 0, which means we have a vector of length 0 that's an integer that won't be used in this assignment really. If you see that, it just means there's nothing returned. The results of influence plot. Oh yeah, let's look over an influence plot, which we will be covering tomorrow and Thursday in class. So influence plots, let's look at one of those. So when a point has influence, like let's talk about how something would have influence in a model. You ready? Points need to have two things to have influence. There's two things a point would have to have influence. Tell me, if I add a point to the model right here, would this point have influence? Would this point... Great. Hey, Emma, we got this. You got it. We'll do that next. We're going to do some of those. You got it. Would a point right here have influence in the model HTT? Would this point right here have influence? And by influence, we're going to mean it's going to drastically pull the model in a direction towards it. It's going to change the coefficients. And you can see if something has influence by adding it, at least visually, to see if it does anything. Very low influence. You're exactly right. How about if I go over here and add a point here? Would this point have influence? Would this point have influence right here? Nope. It didn't even change the model at all. How about, and this one does not have influence. That's the answer to the question. Does this one really have influence? Not really much influence on the model. But what about if I go over here, behind my head? If I go over here and I add a point, why does this one suddenly have more influence? Why does this one have even more influence? Why does this one up here have less influence, but as you go further down, it starts to have more influence? Well, what we have right here is basically the idea of a residual or deleted studentized residual and also leverage. Leverage, think about like a seesaw. If you're here in the middle of the seesaw and you jump on it, you'd probably just push the seesaw downward. Do you see how the seesaw just fell downward, but it didn't really change? Like this is the middle of the seesaw right here, and you jump on the middle of it, and you'd just be pushing the seesaw downward. But what if you went to the end of the seesaw over here and jumped on it? You would do what? The seesaw would suddenly go downward. You're jumping on it right here, and you're pushing it downward. Is that starting to make sense how this all of a sudden has leverage, where this one does not have leverage? But why can't we just go over here and click here and the seesaw goes downward? Now we don't have enough distance in the y direction. So you have two distances right here we should care about. Let's draw on this. And then we're going to do some 201 right after this. So the two distances to care about. What unit ID? Oh, which one, Elizabeth? Are you talking about? This is 320 right here. This is 320 talking about influence and residual, deleted studentized residuals. So this direction right here, away from the mean of the x's, is leverage. So the further out you are from the mean of the x's, the more leverage you have. Having no leverage means you're at the center of the x's, wherever that is. Like if that's the center of the x's, that's like the center of the seesaw right there. The seesaw is balanced on this right here at some point. So what else we need to look at is deleted studentized residual. And that's a very complex thing right here. But that's in the y direction, is deleted studentized residual. We'll put deleted studentized residual over here. So the bigger the deleted studentized residual is, the further it is away from the mean of the line. A deleted studentized residual is specifically when we talk about putting a point in and its distance from the line with it removed. So let's draw this right here again and show that this point right here, its residual is the following. This is its residual. So that's its residual. But its deleted studentized residual, the deleted studentized residual is this. This is a deleted studentized residual if we studentize it. Studentized just means standardized, which basically means we're turning it into a z-score. So let me make a really quick model right here. Let's stop the model. And so when we make this model right here, I'm going to make the same model I made earlier, I believe. Data, body fat, and now we make model, here make a slightly, we'll predict body fat. Tilde weight plus age plus height plus neck might be the same model. Data equals body fat. Oh. Oh, wait. Wait, what? Oh, it's got a capital. That always traps me. So, awesome. So when you look at this right here, what do you notice about this? 2 and -2. Can anyone tell me why, especially stat tool 1? This is, all of a sudden, we're going to start branching into stat tool 1 here. What percent of deleted studentized residuals would you expect to be contained between 2 and -2 most of the time? Like for most models, blank percent of observations would have a deleted studentized residual within 2 and -2. Like, which is not unusual. It's like, yeah, that's not really unusual to be below 2 and above -2. Between this is not that unusual. This would occur what percent of the time? And that's a fine 320 question. Like, between this percent, or about this percent of deleted studentized residuals will be between -2 and 2. That's a question that relates back to 201, but with 320 you should be like, I know what you're doing right there with 2 and -2. Because this relates to something we're doing in 201 right now, 95%. Great job, X, right there. Yep. It's a 95% confidence interval, basically. Like, I'm 95% confident the deleted studentized residuals, we wouldn't really say that, but it's the same sort of concept that we're using 2 and -2. And so this studentized is basically, for all intents and purposes, it is a T-score. It is a T-score, but you could just basically think of everything right here as Z-scores. Like, these are basically a Z of negative and positive 2. So studentized, this word right here, studentized, is basically like standardized, like a Z-score is standardized. And it's called studentized for the student T part of the distribution, the student T distribution, which we will do in 201 also. We won't studentize stuff, but we'll talk about T-scores. So T's are basically Z's, and we would expect about 95%. Oh, let's do it. You got it, Elizabeth. We'll do more probability here in just one moment. And that was X's question 2. You bet. Let's do it. And so when you look at this right here, this point has ridiculous undue influence. This one has some undue influence, and there's a point somewhere over here, I think. It's really hard to see, but there's another one. So would this be unusual, be -4 in this instance? Oh, yeah, and so this one is, this point over here, let me put some more marking around it. This point over here is, it's very far away from the model. Like, this is how far it is away from the model. And then it's super unusual in the X space. So it's very unusual in terms of its X distance, and it's very unusual in terms of its distance from the model. We can't really visualize the model that well, but we can actually look at the check residuals, and we will see it over there probably. There it is over here, it looks like. I think that's the point. There's a second one with a very large residual, so we should see, there's the second one. So you can see its residual over here, and that's its extreme negative residual. You can see like a residual of -18, and looking over here at the influence plot, it also has extreme leverage. To view its leverage, you have to take and look, and I put this in the chat. Check out the morning video where I do the cool code, but we can see it. This is enough right here. I can identify it as this point right here. Oh, this is 320. Don't worry, Emma. We're right about to hop to 201 back. But does this make more sense, HGT? Like, the point we were talking about is very unusual in the X space. And do you see how this person, their height, their X characteristics are very odd? They have a very odd height. That is this person right here. Their age is not that odd, but it looks like their height, and I think that's also their neck. They have extreme leverage because this individual right here has a very, very high neck. I think they're row number 39. If we want to view the person, we can go here to body fat, row 39, and this individual right here, and we only want the first 4 rows today for this. They are, well, that can't be their, oh, their height, no, must be the other person. 2842. Let's see here. Their weight is really high. Oh no, this is them. This is them right here. Their weight is 363. So there's their weight of 363. And then their height might not be unusual. Their height, actually, that's not them right there. That's interesting. That's not them. That might be the other person. But this is their weight. And so that's the really odd individual right there. Is it, hopefully, yeah. So you'd have to look at these characteristics right here. Their neck, oh, we didn't include their neck. And then we'll go back to one here. Their neck is 51. That's them right there. That's the individual right here. That's the individual right there. They carry through on all these plots. That's their neck visualization right there. You could make a histogram of it, and we could see the individual right here if we look at the neck, and that's them right there. So do you see how this individual right here with this neck, of a measurement of 51.2 is very unusual in the X space, and that's what gives something high what. Being unusual in your X characteristics would give you high what for the model. Think about the seesaw. So being unusual in this characteristic would give you very high what, and we're going to head over to 201. So think of that real quick. Great question for the test. Being unusual, or I forgot what I said. So if you're very unusual in your X's, you would have high leverage. I think I'd said you would have high what, but having high leverage means you're very unusual in your X characteristics, and then you can have undue influence on the model, depending if you also have a deleted studentized residual. So deleted studentized residual and leverage are what are needed to have high influence. So keynotes right here, deleted studentized residual, unusual, basically abbreviated to unusual Y and unusual X's. So the more unusual you are in each one of these characteristics, then you can have influence. So influence is having both of these together. You both far away from the model in the Y space, deleted studentized residual, and you have far distance on your X characteristics. Unusual X's gives you high leverage. The bigger these two are, the more influence you have. And that's what this whole plot is looking at back here. The influence plot is looking at the combination of the two. And these are ones that have, like if you go outside of 2 and -2, high deleted studentized residual. If you go above this line right here, high leverage. And so if you're in this quadrant or this quadrant up here, you would have high influence. The size of the circle here is the size of the influence. And this is a super influential point. And it's this person right here who the model does not predict well, large residual. And they're also very extreme in their X characteristics right here. Does that help out HCT? Does that make more sense? I hope it's kind of a good review and good practice of the topics, especially for the test. Let's do the bus stop question. Bus stop question. We are going to watch 3 completely random buses from 3 completely random towns. Each bus has a probability of being on time, better, that's what we like, of 60%. What is the probability that at least one bus is late? Okay, so let's practice this right here. Here's an at least one problem. X and everybody, we got this. Let's do this. So we're going to watch 3 completely random buses from 3 completely random towns. So what am I trying to tell you with this first part of this sentence right here, which is very important to what we're about to do? What am I trying to tell you with this first part? Like, what am I trying to tell you right here? These buses are going to be what of each other? Each bus is going to be what? Each bus is going to be what of the other buses? So it's 3 completely random buses from 3 exactly X, independent. That means if you know bus 1 is late, and I know this is not the way the question's phrased, it just says assume independence, but that's the idea of independence, that one bus being late would tell you nothing about another bus being late. So important here, we need to know this table. This is something we should try to memorize, that when we multiply, we need to have independence between the things we're multiplying, and we need to use the word and. So if we are adding things, they need to be disjoint. And what does disjoint means? It means if one thing happens, the other things can't. Like if you win a game, you can't also lose a game. And disjoint events are very dependent because winning depends on losing. So disjoint is very dependent. So when you look at this right here, we want to look at the probability of, what is it? What is the probability at least one bus is late? So let's draw some buses right here and make sense of this. I always hope I'll like see someone's test and they'll like have drawn out this stuff. I'll be like, oh, that's awesome. I mean, we don't do written tests anymore. So. It's fun. It's fun sometimes looking at a test. You're like, oh, I did that in class and they used that example and that helped them out. Yeah, that's awesome. Okay. Would you agree with me that either all the buses are on time or there's other scenarios where what? Either all the buses are on time or, and I'm doing coloring here to denote purple being late, either all the buses are on time or what? So either all the buses are on time or what? Like we have the instance here where all the buses are on time or what? Either every bus will be on time or at least one is late. So you can just think about like either all the buses are on time or at least one is late. I mean, you could change this problem pretty rapidly to say like 3 students are taking a Stat 201 test. What is the probability that at least one of them makes an A? So we could change this to 3 students right here. So at least one of them makes an A. We'll do that one next. We'll do a second example here, but we could just change it to an at least one problem that way. So we have either all of them are on time, or there's the addition, at least one late. And since this is everything that can occur, it's going to equal up to what? Wrong music. Since this is everything that can occur, it equals up to what? Because we're saying either they'll all be on time or at least one will be late. This has a probability of what now? 1, exactly. So if you write this out correctly, this will really help out because we know either they'll all be on time or at least one will be late. And so now we can just mathematically take and bring this over to the other side here. We're just going to take this and mathematically put it to the other side. 1 minus the probability of all late. So 1 minus the probability of every one of them late. I mean, all on time. My brain broke. So there we go. We're just taking that to the other side, and that's going to be the probability of at least one is late. So, oh, almost works exactly. Probability of at least one is late. So that's the probability of at least one is late right there. So now we need to figure out the probability they're all on time. So think about this. The first is on time, and the second's on time, and the third's on time. What am I saying right here when I say the first is on time, and the second's on time, and the third's on time? So right here, we are just multiplying together these probabilities. So when we think about this mathematically, we're just saying this is equal to the probability of the first being on time, and the second being on time, and the third being on time right here. So that's 0.6 to the third power. And a common mistake is that people often times it by 3, which if you escape 0 and 1, you haven't done probabilities properly. So be very careful right there to make sure to follow through your mathematics. 0.6 times 2, 3, there we go. 1 minus, there we go, 0.0784. Check your work, try to solve it for yourself. Mathematical errors happen. Great job, Lurk X right there, you got it. And so this is just an example of an at least one problem right here. We can totally change this and do another example here really quickly and keep asking more questions. But let's say students are taking to one exam. They've studied really hard. There is a 40% probability. It's not the easiest of exams tonight. It's not... Truthfully, sometimes I think the third exam is easier. I'm not trying to scare anybody, but people asked in class, is this exam harder than exam 1? And I'd say, yeah, and the reason being is exam 1 has a lot of stuff like on mean and on histograms, things you may have heard before. Like, I think before this class, a lot of people knew how to find the mean or knew how to find the median. I'm not saying everyone did, but I think a lot of people, exam 1 topics were things you'd heard, and you're like, oh, I've done that before. I found the mean before. I found the median before. Maybe you'd heard of z-scores. A lot of people probably hadn't, but some people maybe had. And so at that point, it's like, well, I kind of know some of this material going in, so it makes it easier. But when we get to exam 2, a lot of the material is new to everybody, and it's like, well, I've never done this before, so now I don't really have an advantage. When would you take the complement of, oh, good. So going back to the previous problem for just 2 seconds right here. Oh, wait. So for this one, so this is this problem right here. This is the complement, or Marco, does that make sense? This problem right here is everything but all the buses are on time. So this is everything but all the buses are on time. So they're going to be like a car needs to be replaced once a year, twice a year, 3 times. Yeah, I don't think there's one that mimics that. There's more like this, like the Canvas content. That one has a lot more in depth to it on the, it's not a bad question. It's just more time consuming than these right here. That question right there is on the My Pearson, and it's more time consuming than this question is. So check out this one, and Marco, and keep asking questions, Marco, because this one, oh wait, I think you might be asking about this one. Let's look at this one right here. So okay, so what is the probability at least one student makes an A? So what is the probability at least one student makes an A right here? So I want you to think about the 3 students right here. And I want you to think about what, because there's 2 really quick answers we could come up with. What is the probability? And if you write down an answer, let's read off what the answer is. So I want you to write down what could be an answer, and then I'll read it off. Because we have two probabilities right now that we can look at. We have probability of A is 40%, and probability of, you can write not like this, not A is equal to 60%. So if you want to give a try solving this, give it a try. There's two really quick answers you could come up with, and one of them is going to be the right answer. But if you read it off, I think it might be that, Chase. I was thinking, did I just write the same question but with different probabilities? So Chase, I think you are correct, and if you want to put, so Chase solved it, which is correct. I'm pretty sure that's it. So let's take a look at this right here. We want to figure out the probability at least one student makes an A. So we want to see, like, making an A happens for at least one student. Maybe there's one student who makes an A. The yellow represents making an A. So maybe two of them made an A, but at least one of these students made an A. At least one of these students made an A. So the mathematics Chase used, I'm guessing, is 1 minus 0.6 to the third power. So when you read this off right here, and great job, Chase, this is everything but all three students did not make A's. So Chase is saying the instance I don't want to look at is I don't want to see the instance where none of these people make A's. So he's taking the complement of this and saying everything but none of them make A's. Remember, one is everything. One is all possible things that could occur. So when you read this, everything but the instance where no one makes an A. So all other possibilities except students not making A's. So that is the answer right here. What if we change the mathematics here? This would change the question. So if let's delete the question so people don't think we're solving that. What if we change this right here and then try to read this? What would this solve to? What would this, like, put this into Word? This is, and I'll read it in like the way I'd read it. So I'll highlight it as I read it. Everything but all three students make A's. Everything but all three students make A's. Yep. Elizabeth, let's do that. I'll copy paste this one. Let's see. So this is everything but, how would this be in words? I've got that copy paste to go. How would this be right here? What does this mean? Everything but all three students make A's. Yep. You got it, Elizabeth. I will do that next. You got it. Great question. Thank you, Elizabeth. What does this mean in words right here? Everything but all three students make A's. Chase, you're so close. The probability of at least one student not making an A. Because either they'll all make A's, or what? Either every student will make an A, or at least one doesn't make an A. Because either all three of them will make A's, or at least one of them won't make an A. Does that make sense? At least one of those students doesn't make an A. And always read off, everything but all three students make A's. So at least one doesn't make an A. So in great work right there. Yeah, no, you're fine, Elizabeth. This is the office hours that are the hardest. And I do mean this. Like, I literally will say this, are the ones where no one asks questions, where I'm like, so, I don't know what we'll do. We're hanging out. I mean, I don't mind hanging out either, but then I'm just like, I have no questions to answer. So Elizabeth, you were helping out a ton by asking questions. That's what we want. That's like, I don't know. I like questions. Everyone was like, no, I was here one time and there weren't questions. No, you're fine. The worst office hours is when no one's here, when I'm just streaming and no one's watching. And then I'm just like, so no one's here. That's happened like 2 or 3 times where I've streamed and no one's been watching, and I'll choose to do something. I'll like, oh, let's talk about this assignment here. I'll just talk to myself. So you're welcome. What has been the average on the second exam? It's usually in the lower 70s. And we are going to look at the historic average. That's one thing that we're talking about right now. Weights to the 0.784 is everyone but one made an A. Explain more, Emma. I'll solve this question, then we can hop back to that if you like. It's usually about 5-6 points lower. We are going to look at the averages and see how things are going tonight. Like, we're going to be like, how is the exam going? We always look at that. We always want to make sure it's fair. And we've been talking as instructors, like, we start a conversation. Okay. The probability of the bus arriving on time is 0.06. The probability of on time is equal to 0.6 60. That means the probability of off time or not on time. We'll just call it off time. We will say that the bus is either on or off time. By saying the bus is either on or off time, I'm calling these what of each other? These are definitely disjoint, but I'm saying the bus is either on or off time. It can't be both. You can't say the bus was on and off time at the same bus stop, but the bus is either on or off time. One of those two things must occur. Those are disjoint events because if it's on time, it can't be off time. If it's off time, it can't be on time, but they're also what of each other because they add up to 1, which the word. If complementary, yep, they're complements, and complements are disjoint. Are complements dependent or independent? Are complements dependent or independent? So are complements dependent? Great to see you, Sam. Great work. Are complements dependent or independent? Would you say a complement is dependent or independent? Which of those two things would complements be? Is a and that goes for disjoint. They're very dependent. The bus being on time depends on it being off time. So the complements are disjoint. Disjoint things are very dependent because if the bus is on time, it can't be off time. So the bus depends. The bus being on time depends on it being off time. And so disjoint and independent are two different ideas, but it is true that all disjoint events are dependent because, there's an overlap between the concepts. The probability of the bus being on time, got it. There's 3 stops. What is the probability the bus is on time? Assume independence. Why are we assuming independence? So hopefully, if you've done this problem a few times by now, you should know, like, boom, we are assuming independence, so we can do what with these? Put it in the chat, practice up. When you hear independence, you should know we can do what with these probabilities? With this assumption, which is a major assumption for this problem. You might be like, well, wouldn't it be off? No, just assume independence. Don't worry. The problem's like, don't think about it too hard. Assume independence. Don't worry, even I have those thoughts. If you're wondering, but wouldn't it? Yes, I agree. If they are dependent, the probability would be 0. If it's dependent disjoint events, but good question X right there. I'm gonna throw 50 points. The mathematics gets much more difficult. You'd have to do like Bayesian statistics, and Bayesian is like given posterior and prior probabilities. So you could do Bayesian mathematics on this. It gets to be a much more difficult question beyond what we do in 201, but great question, X. And that's what I want to see. I love it when people are like, well, would it be this if this? It would get much more complicated. If they're completely dependent events, then it would be 0. Like disjoint events, you can't have this and this. So X brings up a really good point. Like if we say, what's the probability of winning and losing a game? The probability, like, here, let's do a really quick version of that. The probability of winning is equal to 70 or 90% because your team's awesome. So what is the probability of winning and losing a game? So the probability of, and this is a game where you either win or lose. There's only 2 things that can occur. What is the probability of winning and losing this game? So use the numbers below. What is the probability of winning and losing the game? Good trick question. Exactly, and that's what X was pointing to. Great job, X, right here. The probability is 0. You can't multiply them. You might say, well, wait, you're saying winning and losing. This is the word right here, Brian. But we do not meet the rule of independence. And this is an instance where the probability is 0 because they're disjoint events. There's no overlap between them. You can't win and lose. So as soon as you know you win, you know you can't lose. So you can't win and lose. And that goes to, we can't multiply them. They are not independent. This problem assumes independence, so we can multiply. So X, great job with that. And that's the concept X was pointing out. But that's only for disjoint events. There are dependent events that are not completely disjoint. So, and that's why the concepts are different. They don't like disjoint and they don't mean the exact same thing, but they have overlap in when they're used. Okay. So when we look at this problem right here, we want to figure out what is the probability the bus is on time for at least one of the stops. So what are we not interested in here? I'm going to do some shading. And you know what? Let's help out with the shading colors. So I want someone to explain what we're not interested in. What are we not interested in here? Because we're looking for the probability the bus is on time for at least one stop. So what are we not interested in? We want to look at the probability the bus is on time for at least one stop. What are we not interested in? So we want to look at the probability the bus is on time for at least one stop. So, well, it could be on time for 2 stops, or 1 stop, or all 3 stops. Does it make sense that the bus the times that they are not on time for every stop. And look, if you look at the color coding right here, we're saying the first bus was not on time, and the second bus was not on time, and the third bus was not on time. Does that make sense with the color coding? I'm going to turn this into probabilities here in a second, but we're saying this is the probability all late. So we have either all the buses are late, so probability all late, all 3 buses are late, or at least one on time. So probability of all late or at least one on time. And this would equal up to 1 right here. But does that make sense that either all the buses are late or at least one is on time? Does that make sense, Elizabeth, with this right here? Either all the buses are late, like you've got 3 buses right here. Either all the buses are late or at least one of them will be on time. Which could mean 2, 3, could be one of them is on time, 2 of them is on time, or 3. But either they'll all be late or one will be on time. Yep. So we're just going to algebra. What we're interested in solving for is this right here. So we're going to algebra the other one over to the other side. We're just going to take this and subtract it from the other side right here. So we're going to do 1 minus the probability of all late, and that will give us the other side of the we can just call this y for the time being because that's what we're solving for. So we'll just put here equals to y. Am I blocking that? No, I'm not. So the probability of all late. So we just need to figure out, great job everyone solving in the chat. Excellent work. This is good practice. So 1 minus the probability of all late. The probability of one bus being late is this. There's all 3 are late. So when we read this and people are putting the answer in chat, I will believe the chat. I believe in you, chat. That looks to be the answer. And this is read everything but all 3 buses are late because the probability of being late. So I guess we could do that shading for it. This is the probability of being late. All 3 buses are late, and we're concerned for everything else. We want to look at everything but all 3 buses are late. Does that make sense right here, Elizabeth? And it's open floor for questions again. I'm trying to remember if there was another one we had lined up. But does this make sense for the question and how to think about it theoretically? And you always have, like, you could flip it, but be careful. Like, what is 1 minus 0.6? Well, that's everything but all the buses are on time. So 1 minus 0.6 to the third. Yep, and that would be, so if you did that, think about what 0.6 is. So what did you find, Elizabeth? Great question right there. What did you find, Elizabeth? Because what would 0.6 to the third be? And this is really good practice when you can start to be like, oh, I found this. Like, this is what we want to do. What did you find? I don't want to put the answer here yet, what this is. But you found what? What values or displays would you look at to prove the pairs function, HTT? Great question right there, the pairs function. Exactly, Elizabeth. Great job. 50 points for everyone. And we could do some decision trees. Great job, Elizabeth. So Elizabeth found, what is the probability the bus is late at least one of the stops? So Elizabeth found, because either they'll all be what? Either they'll all be on time, and this is the probability that they'll all be on time. So 0.6 to the third, because this is our probability of being on time for 3 buses. So the first is on time, the second is on time, and the third is on time, and everything but they're all on time. So when we think about either they're all on time or at least one of them is late, I think, Elizabeth, I'm hoping it's clicking right here, like, oh, either every bus is on time or, because we're doing 1 minus it because it's the other side of it, either everything's on time or at least one of them is late. The z-score formula will be given to you. And this is the probability at least one bus is late because either they're all on time or at least one bus is late. Should we do decision trees, everyone? I think we got good stuff right here. Oh, and then Kennedy wants P and P hat. So, and then, yep. My eyes are blurring. Awesome. Great job. Great job, Elizabeth. And I will say this, please, and this is my quick Brian begging you. I'm going to hop over here. So will we get a variation where it says at least? No. Good question right there, X. That requires permutations, which I can, it actually does the addition rule if you do it, but no, the answer is no. So you won't have to worry about that. We'll do at least one. We only do the at least one problems in this class, but you can calculate those, but we don't do them anymore. We used to do them like 7 years ago. But I do want to say this, little music here, and then we'll hop over and do the PP hat question. But we're back. I try to give advice. Are we back? I got the really rare stream is disconnected. Are we back? Are we streaming? We are back. Streamlabs actually literally said stream has disconnected. So sorry about that. That just really randomly happened. I promise I didn't click anything, but we are back. Yeah, that was a Streamlabs disconnecting. If it disconnects too long, it actually ends the stream and then starts me randomly streaming on YouTube again, which one time there was a video of me being like looking around trying to figure out what's going on. I was like, oh, it says it's still streaming. What would I recommend you do before the test? I would, if you've been studying a lot, put on some of the review videos and just relax. Even if you don't put on review videos, just relax. Like, just take a moment. Like, I mean, there's only so much you can do to prepare for a test. And some of the preparing for the test is going to be just relaxing and just like meditating and calming your mind. Everyone knows what's best for them. Like, some people are going to try to like have that book open right before the test and just be like, gotta put the last few things in my brain and then just, get it all out. I know, Emma, I think the best advice is this. No matter what happens tonight, like, let me tell you this. No matter what happens tonight, there's a lot of opportunity left in the class. No matter what happens. Here's what you want to do. Let's say tonight doesn't go so well. It's Brian's advice for the test. If tonight doesn't go so well and you were to make like a 60. Some people make below a 60. Like, if you make a 60, here's my advice. I think we have the grade calculator, right? Project 2 is coming up. We will work through Project 2. I will do pretty much everything on Project 2 here on the YouTube channel. So come here, ask questions. Don't try to do all Project 2 on your own. Don't be like, I'm going to sit down on my own. I'm going to do all Project 2. I'm not going to ask any questions. Come here to the YouTube channel, ask questions. Be like, hey, Brian, does this look right? Hey, can you explain this part? Come here, ask questions. It'll save you time because I'm sure you have a lot of stuff with other classes. The tests are the hardest part of this class. Well, what else can you do to help mitigate that? My Pearson, which we've extended those assignments. Homeworks, quizzes, Canvas content quizzes. Your goal is to get as high of grades in everything else because the tests are going to be the hardest part. The average grades, I can go look at it right now if you like. Well, I wonder if I can get that pretty quickly. Last semester, the average grade in Stat 1, which things stay pretty level. I will tell you the average grade in Stat 1. What the heck? I'm not the primary instructor of those courses? Okay, that actually makes me a little afraid. Oh, published, no. I was like, what? Did it take away my courses? I would have been really sad. I don't even know what year it is. Man, that's bad. When you get old and you're like, what year is it? What year was last semester? Last semester. Okay, we're not streaming that. Okay. Last semester. The median grade. I'm going to have to sort the grade book here. I wish it would just show you the grade distribution. Sort by. Still loading. It takes a while to load in all the grades. The median grade. And we're good. Okay, it's finally loaded in. I'm going to go about halfway down. Someone got 100.3 last semester. Someone had 100 also. There was 100, 100.3. Halfway down the grade book, the median grade is literally a B. And the amount of... There are some Fs, there are some Ds. But the median grade is literally a B. Lots of Bs. So, yeah, the median grade looks to be about an 85. And so the median grade's about an 85. So it really comes down to the work. How do these bonus points transfer? You got it. And if you're in the asynchronous class, so you can check your points at any times, you can look at Camden's points, right? Like, as long as you're okay with, like, if you don't want to check your points publicly, you can be like, everyone wants some points. But a B is an 82. And what do you need with your bonus points? Here, we'll play one more song. We're just getting some positivity in here. We'll put on a more positive song. This one's a good one right here. So what do you need to get the B with your bonus points? Which keep coming to class, keep getting the bonus points. Some people are on the prestige mode already. So keep showing up, get those bonus points. We'll throw out 50. People need some bonus points right now. So what do you need to get a B with your bonus points? Like Tyler right there has already got his bonus points. He's getting some bonus points right there. 3,000, yep. And so you can check your bonus points at any time. I set the bar not too high for it. I think I have 99 right now on A stat. Yep, and then the asynchronous can also do the flashcards because they're not required to watch this. So if you are seeing this right now in the asynchronous class, you are not required to watch this or like attend any live lectures because you're in the asynchronous class. And I'll have your module posted probably tomorrow night. Sorry, working on it still. busy. But you have a week to do every module that gets posted. And I think we'll probably be having it on like Wednesday because great job. And so you will have all the points just by doing that. And then if you're attending this is just bonus on top of it. And I'll send out a form saying, if you're using a name other than your usual YouTube name, please make sure you know, like, I know which one you are. So say someone may have like 2 bonus points. How does that transfer to the final grade? 2 points. 2 points. That's how it works. That's your points. So your points you see right there are your points. It's like Pokemon Go where the levels up are slower. I'm in your asynchronous. Yep. Oh yeah. Tyler, do this. So I don't mod people during the office hour stream because anyone can join. But Tyler, with the links, next time you see that we're streaming, join one of those links, and then I will mod you during a live class. So use one of the live links, and I mod as many people as I can during live class. Does that make sense, Tyler? So join, so that way I know like someone has access to the links. My greatest fear is someone gets modded and then starts like deleting people and starts like hiding people on the channel. And someone's like, Brian, you never reply to me. And I'm like, no, someone hit a bunch of people on the channel. So I think I can see if it happens live though. They'd have to like, I don't know. No one's done anything like that weird, which is really good. So it just lets me, yeah, Tyler, you got it, man. Just click on one of those links and be like, hey, Brian, mod me. And I'll be like, you got it, Tyler. You got it. So I've like made it a rule for myself, even though I'm like, I want to mod people. We got a few non-stats winners who are mods, like Calzo and Tyrone. And yeah, so awesome stuff. Let's talk about the difference between P and P hat. But my last bit of advice, no matter what happens tonight, stay positive. Keep doing the My Pearson. Keep doing your homework. Keep doing the visualizations. Because it really comes down to, and I mean this, the difference between, do I have that grade calculator? I've got it on the site. Let me go grab it. 2 seconds, everybody. I'm going to go grab the Stat 1 grade calculator. Let me talk about the asynchronous for a second here, and then, because this is like super important. I know we need to cover more material. I've got a bunch of videos over those, but I want to make sure people know, especially the asynchronous. For the asynchronous, let me pull up the asynchronous grade calculator. And so the asynchronous grade calculator, if I can't make more of a plea to you to please, please, please do the work, you'll see it right here and you'll be like, whoa, I need to do the work. So here's my plea to, this is the asynchronous class. Yep, it got bumped to Sunday, yep. So asynchronous, if that's how you spell it, this is the asynchronous class. Let's say tonight's exam does not go well and you end up making a 60 on tonight's exam and you made a 60 on this. And if you do all the other work, which I think this should be, did I do these properly? Yeah, good. Those are proper. So what do you notice about this right here? Just like the Canvas contents, Catherine, great question right there. Like the Canvas content. I swear my Pearson stuff is hard in the last exam. Yep. My Pearson can be harder sometimes than the exam. And what do you notice right here? Or let's even go lower. Tonight you make a 50. My gosh, are you serious? No way. What have I done? This is insanity. Actually, I'm actually like, maybe I need to adjust this for next. I am just like amazed by this. Yeah. This is insanity. Just check this out. I know, and this is the thing I want people to know. And it's like, please just do the work. Please do the work. Please do the assignments. Please do the visualizations. Please do. This is a person who's failing every test. Now, this is the asynchronous, though. If this is the asynchronous, this is you. You have the module section, which counts 15% of your grade. Yep, there's the final right here, and this is the asynchronous weighting. So, no, please. Well, we won't. I can't readjust now because we got a syllabus, and that's the rules of it. So this is not getting readjusted. So, but if you're in the asynchronous, and this, please do note, this is asynchronous. This is not the synchronous class. I'm gonna do, Exactly. So X, you're doing the right thing right there. And look at, like, I mean, that's it. This person who makes a 70 on all the tests and does all the work, and there's also extra credit on the second project, something like that. I mean, now you can even go here and do this. Yeah, that's literally about the cutoff. What do you notice right here? If this person gets all the bonus, and they do all the work, and they get the extra credit on the project, and they do all the work, you can make C's on all the tests and still make an A. Hey, Kayla, good to see you here. So if I am to stress to you one thing, there is multiple choice on the exam. Catherine, great question. Just like the Canvas contents have multiple choice, the Canvas contents are always going to be your best kind of like preview of what the test is going to be like. Exactly. There's a lot of willpower. I've had a lot of very intelligent friends in college. I'd like to think I'm very intelligent, but if you don't put in the work, then the grades are not as good, because all of a sudden now you've got a person who's making 80s on the tests, but this person here, they don't do the quizzes. They start putting in the quiz work there. The modules, they're not watching them. The homeworks, they don't do them. The visualizations, they missed a whole bunch of those. Some people have low visualizations, not the end of the world. Canvas contents, they're doing them last minute and not doing great. They forgot the first project. They turned the second project in late without help. And then they don't. What if this person doesn't have any bonus? This person got B's on all the tests. And now they might make a D plus in the class. Mm-hmm. We did a simulation earlier. We'll check it out. Any chance you can send that to my math piece anywhere? Maybe he'll take your lead on grade. Yeah, no, thank you, Kayla. Like this is the asynchronous class has a lot of like do the work. That's so mean. I'm not trying to be mean. Please do the work. Brian, you're the teacher. You can tell us to do the work. Let's take a look at the regular stat one here for a second. Where is it? Oh wait, gotta go to modules. Okay, so we found out you basically need to make C's on the test if you're doing all the work to get an A in the asynchronous course. Do all the work and make C's. That doesn't mean if you do most of the work and you make C's, you'll make an A. But the goal is like do everything you can to the best of your abilities. Life does get in the way sometimes, but the more work you do, the better you're helping yourself out for the test. I've taken Calc 3. What stats class uses that? A lot of upper level statistics use either linear algebra or calculus. We do more business analytics these days because we had some really great questions yesterday. Some people are bad at yes. Clarissa, thank you, Clarissa. Let's throw some 50 points for positivity, Clarissa. Thank you so much. There's a little more weight on the tests over here. So Clarissa's right. Let's look at this. 100, 100, 100, 100, 100. I should have put like a note out of 10. 105. I know it's very optimistic here to say like you'll make 100 on everything. That's very, very hard to do. But let's say you were to make 75s on the tests. You'd have an A minus. So there's not the module section on this. The tests do count more. It looks like you need to make basically high C's on the tests. Your lowest mark is basically a high C average on the tests. So the asynchronous has like a low C mark due to they have the modules that they need to do because they have to watch the modules. If they don't watch the modules, they lose a large portion of their grade. But this is the synchronous class right here, has the basic, that's about where the cutoff is at with your extra credit bonus. Like if this person does not do the extra credit bonus, I would probably still give them an A minus, but I'd be like, oh man, I'm supposed to not. Because you get your bonus by how many you do. And I think everyone knows how to check your bonus points. And the asynchronous class has the flashcards that they can do instead of watching lecture right here. So, and hopefully this, like Emma was saying, I think it was Emma saying, this can hopefully bring a little bit of, okay, even if tonight's exam just goes ridiculously bad, there you go. Who here just breathed a pretty good sigh of relief when you saw this right here? Like, we went from tonight's exam going, I mean, not horrible. I mean, 78 is not the end of the world. I mean, it's like, oh man, 78, C+. But you're welcome, Emma, because right here, even if the final and tonight's exam, if you have the bonus right now, what do you still have in the class? What do you have if tonight's exam goes bad and then the final goes bad, but you're doing all the work? What's this person make in the class? I want the A too. I want to see everyone make an A. And the best way to make the A is to do all the work, prepare for the test, and if the test goes poorly, you can still make a B. It's all right to make a B, I promise you. I mean, I wish a lot of my queries were Bs. You have at least a B. So this person right here, they're just the non-test taker person. But what if this non-test taker person turns into the person who gives up on my Pearson work because it is going to be a little more difficult. I am going to do them during office hours. You just saw that grade took a major hit. They stop doing the homework as much, the visualization, they forget the last few, the Canvas contents, they start not doing those. The project, they don't come and get help. All of a sudden, they're dropping to the C minus range pretty quickly. You just saw bigger hits on that than you did by me adjusting the test, because all those are just like, just a million sort of just like taking it down each time we do that. And this person right here maybe is the person who's losing hope. And all of a sudden now they're in the D plus. If they don't have a bonus, they'll get a D plus. They'll have a C minus. And they might have to retake the course. So look at the drastic changes that occurred. Now, let's say you're someone who you're doing everything, but you're an individual who forgot project 1. Well, even with forgetting project 1, you'd still be at a B minus. You're really close. Let's just say you did a little bit better on this test right here. Yeah, you're definitely, you only need to do a little bit better. You could have forgot project 1. There are some people who missed project 1. You could have missed project 1, and by the way it's weighted, you could still make a B minus. You're doing all the work. You just, I forgot project 1. Brian, I just can't believe it. It happened to a few people. You're still fine. Don't worry. Not the end of the world. What's the most important thing? Don't give up. Don't give up. Don't give up. Does anyone want me to run any grades in here for these synchronous? I don't round up grades. I use your bonus. So the bonus is even better than rounding, but it requires. So if anyone wants to look at their points right now, you won't get rounded up. There's no rounding on your points. You get what you get. But I mean, I do sometimes. Well, thank you there, Reagan. I mean, if you're like 89.99999, I always, when I look at the grading book, I always like draw a line in the grading book, and no one gets like, I make sure that like my A range, or this would be A minus right here. So there is like a very distinct line. No one gets a higher grade than anyone else, but I'm not going to give that person a B plus. If that's what you have with the bonus, but there's no rounding on it. So there is no, I can't give that person a B plus. Would I get anything with like 400 points? What's the cutoff for an A again? 90. But I'm going to give that person it. That's so it's 92 is the A. So that person would get an A minus. I'm gonna give them the A minus. Does anyone want me to run any things right here? We had a few more questions about like what is P hat. I can cover those, but I hope this gives people less anxiety. It'd be great to make 100 on the exam tonight. That's going to drastically change this. Now you're at a B plus. So all of a sudden, if you ace tonight's exam with everything here where you do poorly on the final, if you have the bonus, you're at a B plus. It's obviously better to do better tonight, but you're not going to destroy your grade. The biggest thing is going to be what you do after the exam. Like, do you keep doing the visualizations? Do you keep knocking out my Pearson and doing a great job on those? Do you keep doing the Canvas contents? Do you do project 2 and get the bonus? All of those are going to have a bigger weight on your grade than tonight's exams, like the Canvas contents, the visualizations, the continued work on the homework. All of this right here is 17, 22, 28% of the grade. So 20% of the grade, basically double tonight's exam. Exam 2 might be the hardest. Great questions right there, Reagan. It's just because exam 3, I think, is a lot of repeat material. And let's actually show that. Here's an equation for exam 3. Let's start learning some exam 3 material. Here's an equation for exam 3, and I want to see if you can tell me. And this even brings us back to talking about exam 2 almost. Anyone notice right here what this almost looks like? And what are we finding right here? Does anyone know what we have found with this equation? By taking the sample proportion, which would be like if we speak to 100 students and 20 of them own dogs, that's going to be the sample proportion. How much are we getting? 90 minutes. You have clarity, you got it. Random question, but what was the format exam? Like the Canvas content, great question right there, Edward. Just like Canvas content, multiple choice, true, false, all that stuff. X, you're so close, not A, and you'd be right. I'll show you one that is a T-score. It's going to be a Z-score, which you're basically right. It's not all multiple choice, true, false, numeric entry, like Canvas contents. So what about if we do the following? Y bar minus mu naught over S over square root of N. Look, X was right here. This is a T-score. What about if we do the following? Y bar minus mu over sigma over square root of N. That is actually a Z-score. And we do give you these formulas. What do you notice about all these formulas, though? Like, look at the first part. The first thing is always what we see in a where. That's a sample mean. That's a sample mean. The top one's a sample proportion. So the first one is always what. The first part of that equation is always what we see in a what, which it's just like the formula observation minus mean over standard deviation, gives us a z-score, is what we see in a sample exactly. And then we're going to take its what from another value. We're taking its what from another value. The top part of this equation is just a what from the other value. Could you go over, yeah, let's do some true false next. You got it, Nolan. Great question. We're going to take its what from a value, because this is all test 3 material. It's all test 3. And it's like if you start to see how it works, sample minus actual, but that's basically it. We're standardizing the distance. So we're taking a distance it is away. What's the difference between the actual and the observed, or the observed minus the mean of the distribution? So we're taking the observed minus the mean, and then we're standardizing that distance on the bottom right here. The bottom of this is just a way of standardizing those distances. So when you look at the bottom right here, this is just a standardization of the distance. So we're going to take that distance and standardize it. Do you provide set to one students with inference reference for? Oh, wait. Kayla, if you have that, send that to me. We should post that, and I'll ask Terry. Why don't I not have that? Send that to me, Kayla, or I'll ask Terry. I know Terry. But I don't have that. I bet it's really good. I bet that's a really good sheet. And what is the difference between standard error and standard deviation? Standard deviation is for a sample. Standard error is for a sample, and standard deviation is for the truth. Email me that. That's acting. I think that's on your local drive. I think that's on your local. I think that's local to you. So I don't know if that would work for us. Email it to me or Discord it to me. I'll take a look at it. Thank you so much, Kayla. And so the difference between, we mentioned this earlier, we want to do some true falses. Let's do some true false to NP and P hat. So P hat is always going to have with it a what. Whenever you see P hat must have a what. P hat's always, I got it from the SSI. Oh, that's so awesome. Thank you so much, Kayla. P hat's always going to have with it a what. You must always have this with P hat. P hat's always going to have a sample size. So the P hat having a sample size. So each of these have complements like P hat and Q hat and P and Q. But each of these has a sample size with it if we have P hat. Where we have P, we have for the whole population. So that's for all observations. So if I were to say something like, the registrar knows that 20% of students live on campus, is that P or P hat? The registrar knows that 20% of students live on campus. Is that P or P hat? The registrar knows that 20% of students live on campus. Is that P or P hat? That would be P, because that's the truth for everyone. So when we say P, we're talking about for all students, for the whole group, for everyone. What if I were to say something like, the state of Tennessee has information that 70% of people have a driver's license. 70% of adults in the state of Tennessee have a driver's license. Is that P or P hat? There will be some math-based ones. Yep. Definitely, Tyler. Great question, Tyler. 70% of people in Tennessee have a driver's license. Is that P or P hat? 70% of people in Tennessee have a driver's license. Is that P or P hat? So then you have to ask, is Brian talking about the population or the sample? Thank you so much, Kayla. You're awesome. So this is population, the population proportion, and this is the sample proportion. So is Brian talking about the population or the sample? It would be, we're talking about P right here. So does P have connection with the margin of error like P hat does? So the margin of error is made from samples for confidence intervals, because if we were to go out and take a sample, this kind of bridges the topics and we're going to do true false. When you make a confidence interval, you're trying to estimate P from P hat. So when we do a confidence interval here, we do not know the truth. We're trying to estimate the truth. Like, let's say we want to figure out how many people are going to vote for us. So we go out and talk to a sample of people, right? So how many people did we speak to? So how many, just make it up. How many people did we speak to? We go out and poll blank amount of people. So let's put that on here. We go out and take a poll of how many people. This is kind of how it works. We go out and take a poll of, let's say, that's too many, 400 people to see if they will vote for us. From this poll, how many vote for us? So how many say they will vote for us? How many say they're going to vote for us from this poll? So from this poll, how many say they will vote for us? So from this poll, how many say, great job, Kayla, right there. From this poll, how many say they'll vote for us? From this poll, how many say they'll vote for us? You can just make it up. Whatever you want. There are numbers that don't work. Anything outside of 0 and 400 don't work. 187. Yep. 187. So now the first thing we want to do is identify the notation. So identifying the notation is key to solving any one of these problems. Go ahead and write the notation in the chat for any of these. Can you solve for all 4 things? I'll write an additional thing right here. Make a 99% confidence interval using the z-score of 2.5758. That would be given to you on the test. So identify all 5 things that we would put here for notation. We have 5 things we need for notation. What 5 things? Correct. P hat is going to be x over n, and then you can solve from that for q hat. So we have right here, this is x, that is n is the sample size, x is the number of successes. And yep, great job, Kennedy, and great job, x right there. So we have 187 over 400 is equal to p hat, because that's what x over n is equal to. So p hat is equal to, let me think right here, 45, 46, 46.7, I think, 0.467. So 187 divided by 0.467. There we go. 0.467. And then we need the complement of that. There we go. And then we need the complement of that for q hat. So q hat is going to be equal to 0.5325. How do we find that? 1 minus p hat right there. Great job, Licker. That's amazing work. Good practice. So we see right here, there is q hat and p hat add up to 1. And we just plug in the numbers. Now, what is the point of this formula right here? Like, what's the whole point of this formula? So what is the point of this formula when we plug in the numbers? What are we trying to understand? We took a sample of people, and what do we want to know? Like, why are we took a sample and asked them, are you going to vote for us? And then, so what's the point of this then? Like, what is the point of creating this interval? So we took a sample and we said, are you going to vote for us? And then we found 46.75% of the sample said they would vote for us. So then what's the point? What's the whole point of this interval? Like, why are we doing this? Why are we here? Why are we here? I don't know the rest of that quote. I should put that on my... So many things I want to put on the soundboard. Does anyone know the rest of that quote? Why are we here? So, well, we're going to find the margin of error. That is very correct. Brian's losing his mind. So, there we go. Divide by 400. And we take this. So that's that portion. We just solved that. I'll vanish. With the level of confidence, you think that exactly X, you're on the right track with this. Now we're just going to multiply this by here. 5758. So we now found the margin of error, and this is the margin of error for this question. And so the whole point of this question is to do what? To understand the true proportion of people who will vote for us. We're trying to estimate, like, when the election happens, what is the true proportion of people that vote for us? What is our best guess of the true proportion of people who will vote for us? Our best guess comes from the what? So here's the interval right here. It's going to be 46.75% to plus or minus this. So we would just add and subtract that right here. And so let's write a true or false. So let's do a bunch of true false questions. Hang out, play the true false game. We'll end with this right here. A confidence interval is made from the population to estimate the truth for a sample. True false. Too big a font. I'm going to write 5 true falses. We did decision trees in another video. Sorry, I didn't do decision trees today. Okay. Here we go. Hey, what's up, Mary Beth? Good to see you here. I'll reappear. So if you have high confidence, that means the interval is bigger. If you have lower confidence, you have a narrow. Yep. So confidence, just to Lurker's question right there, confidence is going to control the z-score, which is part of the margin of error. So when you increase the confidence, the z-score gets bigger. So when an interval is, let's put a question here on that. Okay, great stuff. Awesome stuff. Let's start with the first question right here. So go ahead and true false this one right here. A confidence interval is made from the population to estimate the truth for a sample. Morgan is saying this is false. What do other people say? I mean, maybe you're right, Morgan. I wouldn't. Yeah. So Morgan, what is the actual idea right here behind confidence intervals? Because this is very false. Morgan, you're 100% right. I promise I wouldn't be like, maybe Morgan's right. It's if I say maybe, I have a lot of cues that you can figure out if someone's right when I'm like, maybe that's right. And then it's like I'll be like, well, let's, like, yeah, this is false. A confidence interval is made from, we'll change it to true right here, a sample to estimate the truth for a population. So it's got it reversed right there. Are we going to have to, oh no, Robert, good question right there. Like my Pearson problems, I hate those ones. Those are some of my least favorites. No, good question. Only on the my Pearson problem, we don't luckily have test questions like that. Good question right there. Test question won't look like that. But test question won't look like that. Good question. Like, yeah, I'd want to know that too if I was a student. No, boom. I hate those my Pearson problems. They're tough. Simple random samples, take large groups and sample everything in the group. That sounds a lot like what? When you hear this idea of taking a whole bunch at once and doing a census on it, you should automatically be like, whoa, we're talking about what now? This should just like alarms going off in your head, be like, wait a minute, take a whole bunch at once and sample everything in there, doing a census on it. Sounds like cluster. Yep. This is false right here. We would take random clusters and do a census. So you should immediately start to identify right here that this is a census, and the census is associated with a cluster when you take a large group and you're going to do a census. Now, you do take the clusters randomly. That's not a multi-stage. So when you take large groups and sample everything in that group, you are doing cluster sampling. So we don't want to be tricked by that. Two events that are disjoint can be multiplied together. I mean, you can... Maybe this would be, we always talk these things where we're like, should be multiplied, or since two events are disjoints, we can multiply them together. Should you assign numbers and randomly select numbers for, yep, you are correct, X. That is how it is done. We're just randomly taking, like, if the registrar randomly takes student IDs, then that would be a simple random sample. If we said something like, the registrar takes random IDs of students, as long as they're doing it randomly, because we got random numbers, so they could generate a random list. Everyone is getting it. Nice job. Nice work. This should be add right here. To make it correct, it needs to be add two events that are disjoint, or what if we change this over here? What could we change disjoint to right here? So we could say two events that are what can be multiplied together. So we could change that to add, or we could change disjoint to what? Like we could also change disjoint to make it correct to independent, exactly. So we could change this to independent. So either of these would make it true, but it's currently, as it states right now, is currently false. So there's a lot of ways to write it as a false thing, but we could write two events that are independent, can be multiplied together, or we could put two events that are disjoint, can be added together. But in its current state right here, it is very false. And for a review of this, please make sure you have this. I would write this down. This is a great table right here that shows you the math, the word, and the rule associated with it. So make sure you have that written down. Pause the screen. All's good. Option. Two events that are complements are dependent. Well, it often helps to think of an example for this and to see if it is true. One of the best ways to do this is do probability of win or probability of not win, which, usually means lose, but that's the easiest way. That is mathematical notation for not win. And so the probability you win because you're awesome. No, you're not, dude. Don't lie. You're still awesome. I believe you are. So these are two events that are complements, and are they dependent? Yes. They're also disjoint. Things that are disjoint are also dependent. Complements are disjoint. But do realize that disjoint and dependent and independent are different things. It just happens that complements are disjoint and complements are dependent. So this is very true. Because what are you saying? You're saying winning depends on not winning. So winning depends on not winning. So this is very, 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 very true. Next, let's look at next right here. A decision tree takes categorical Ys and quantitative Ys, or can. So a decision tree can take categorical and quantitative Ys. True or false? Correct, X. You are right. Yep, same words right there. Let's put that right here. That is true. Those are the same thing right there. I just put that as a note right here. It is very, very true. I just want that on the screen. This is true related to the last one. Those are all the exacts. It's just a different, they got to have different words for them, right? To make it more confusing. You are correct. What is the only thing we do not put in decision trees? What is the only thing we really don't want to put in decision trees? We don't want to put this in or things that act like this, which means they have lots of levels. Because you could say like, what is your favorite ice cream flavor? Like, oh man, everything but the kitchen sink is so awesome. I just want to get that. We got groceries today. They went through their 3-day quarantine. I'm crazy. When an interval is more confident, it becomes less precise. So an interval becoming more confident, how would that look when an interval becomes more confident? An interval becoming more confident, at least with what we have right now, will not change the mathematics much, is going to change this Z star right here. So the Z star is the percent of confidence, and you'll notice that the Z star is part of the margin of error. And what happens if we become more confident? Well, becoming more confident is going to do the following. Instead of using like a 95% confidence interval, we might go all the way up to like a 99.7% confidence interval. So 99.7% confidence interval would go even further out right here. And you notice this means the Z-score is going to go from like -2 to 2 to -3 to 3. And we have a lot wider of an interval. So an interval becomes more confident, it becomes less precise. Does it make the margin of error bigger? Yes. Yep. That's what we mean by more confident means bigger margin of error. So more confident right here, we're saying this will have a larger margin of error. Everything else similar, so bigger margin of error. And so bigger margin of error. Because this right here is part of the margin of error. Wrong color. Change places. So that is part of the margin of error right there. So by changing the Z-score, it is inside of the margin of error. And if you make the Z-score bigger, the interval will become more confident and it'll become less precise. You're basically making your interval go wider. So good concepts right there. Some of the last concepts we were covering. Do people feel a little bit better? And also we know if test grade's low tonight, not the end of the world. Believe me, everyone, when I see people making 90s and above on the test, I'm like, yes. And when I see low grades, I'm like, no. I've already seen a few and it hurts. I don't like it. I don't want low grades. So this is random, but can you explain X and when solving for it? So in our examples, let's go back to this one right here. So when we have X is going to be the number that respond in the affirmative. So when you think about what X is right here, we talked to 400 people, and so that's the sample size. And then anytime we have P hat, we must have a sample size associated with P hat. So notice here how P hat is always going to have, I'm going to review the tape because I swear I had that pen highlighted. Anytime we have P hat always is associated with a sample size. So you always need a sample size associated with the sample proportion. Does that make sense, Hannah? So the sample proportion always comes from a sample size of a certain amount. So let's say Brian were to poll UT students and ask them, so I take a poll of UT students and I ask, is your favorite flavor chocolate ice cream? So if I ask UT students that and I talk to 500 students, did I just find P hat or did I find P? Glad to hear that, Kennedy. If I ask 500 UT students that did I just find P or P hat? I talk to 500 students and the proportion of them that like ice cream would be P or P hat when I talk to 500 students. So if the grades are high, the grades should get higher, right, X? I'd love it if they're above an 89. Maybe we should, I'm just kidding. And X is right, it'd be P hat because that would come from a sample. So if we talk to 500 students, instantaneously like, oh, that came from a sample, that's the sample proportion. What if UT claims that the true proportion of students that like ice cream is 40%, like chocolate ice cream is 40%. If UT claims the true proportion of students that like chocolate ice cream is 40%, are they making a P hat or P claim? Which of those are they making? If UT claims that the true proportion of students that like chocolate ice cream is 40%. So if someone said like UT claims that the true proportion of students that like chocolate ice cream is 40%, would that be P or P hat? It'd be P. And notice I gave no sample size. Now you have to watch out because then the question might say, like, here's where people usually get confused. UT claims that the true proportion of students who like chocolate ice cream. No, we're doing Rocky Road. No, we're doing everything but the kitchen sink ice cream is 40%. UT claims this is true. You sample 100 students and find that 38. Yeah, let's make it harder. Sure. Okay. Find P hat. And I guess we could do it proper. What is P here? What is P hat? Well, we have to know the difference between a parameter statistic. And this is actually a great question for that right here. Because the top one is a parameter and the bottom one is a statistic. So the top one being a parameter means this comes from a population. That's the truth for a population. And the bottom one being a statistic, we'll change colors here. The bottom one being a statistic means it comes from a sample. So parameters are the truth for a population. I believe that's correct. People are finding the right answers right there. Correct. And so the sample statistic for this is going to be people are finding X over N, which is accurate. This is related to the sample statistic. And then this right here is going to be the parameter for the population, which is apparently the truth. So to find the sample proportion, we have to take X over N, which is going to be 38 over 200, which people are finding is equal to. And this is way off the claim of the population, what apparently is true. So this would probably be very unusual. And the good news about finding this out is if you know how to do the formulas, very, very quick solve on this. We could go right here and do P times Q over N square root. That's the standard deviation. We go to our David and Elaine applet. And so we can find out if this is unusual, which, yeah, this has a z-score of almost like 6 or 7. Yeah, well, we just found the standard deviation. So is this unusual? The answer is yes, because we have P hat minus P over P times Q over N square root. And that's going to give the z-score. And our sample is 19%. Our truth is 40%. And then the standard deviation, which is P times Q over N square root, is 0.034. And that's going to be a z-score that's crazy huge. That's going to be like a 6 or 7 z-score. Maybe 5.8. 5.8, I say. Negative 5.8, technically. 6 point. I just said 6. And that's the z-score for how unusual it is. And that means our observation was 6.06 standard deviations below the mean. And this is going to be off the scale. And so what I did really quickly right there, very, very quick review on that, is I solved for the mean of the distribution. And I solved for the standard deviation. That's a very quick solve. If you followed that, you're probably very, very set for tonight. I don't expect people to follow that question as quick as I did it. I don't know. Sometimes I want to solve stuff. What questions? PPSS, yep. Population parameters, sample statistics. So what questions are there? The notations on the screen. Let's go until like 5. It's almost test time, right? Do we have a bunch of people? Like, I did one way too fast right there. I actually feel bad. 37 viewers. Thank you, everyone who's here. Thank you, everyone who's here. What questions are there? Will we have to solve for the z-score? You might have to. If you notice right here, we took the, look what, I can't speak, I'm losing my mind. The conditions, yeah, let's do conditions. Those are ones we can get down pretty quickly. And we take the P hat minus the P, and the standard deviation was P times Q over N square root. So that's the standard deviation right there, which I'm slightly blocking. So what time is the test? 6 p.m.? Yep. So we're getting closer to test time, and that'll get us the z-score. Let's review the conditions again and see where some conditions fail. Here we go. Let's do conditions. Condition 1. Random. Condition 2, 10%, less than 10%. I call it 10%. Condition 3, success failure. Okay, let's talk about when these conditions would fail. Yeah, Madison, I bet we can do that. I think we did it earlier, but let's see here. We'll do that here in a moment. You got it, Madison. So the mean always equals P, correct. For the sampling distribution for the sample proportion, Lauren, that is correct. The mean is equal to, as you just said, P for the sampling distribution of the sample proportion. Yes, for that, correct, which is chapter 13. Yep. But there's other chapters. Don't worry, test 3 material. I just don't want you to think it's always that. So, but for this test, yes, for the sampling distribution sample proportion. We go to the M&M factory, and they make 10,000 M&Ms a day. We decide to take a sample of 2,000 M&Ms, and 400 of them have W's instead of M's. Can we make a confidence interval to estimate the true proportion of W's? You know, it might be about half of them. There we go. Half of them have W's, half of them have M's on them. So can we make a confidence interval right here to estimate the true proportion of these M&Ms that have W's instead of M's on them? So, I think it's about 50, 60 minutes right now. About 50, 60 minutes is the mean. Do we meet the conditions right here? Ooh, we did. Whoa. Sure, I'll let that one. If I didn't put that, I would actually, yeah. So where do you think the issues are right now? Where are the issues with this? Do we pass everything now? You are correct, X. That's the thing I wanted you to notice. You could have said, wait, it's not random. But we've sampled 2,000 out of the 10,000 M&Ms, so we do not meet the less than 10% being sampled. Does everyone see that right there? We sampled 2,000 out of 10,000 M&Ms. We do not meet the condition right there. So this is a good example of not meeting the condition there. Is everyone good with this? I don't want to do things too quickly. I want people to see this does not meet the less than 10% of the population being sampled. We could do another quick version of this where we say something like, we go to UTK campus and we talk to 28,000 students because we get almost all of the 30,000 students sample. Can we make a confidence interval for the true mean distance they are? Now, if you notice, this is not something we've covered yet. You bet, Noah, you bet, yep. So this is not something we've covered right here. It has a different third condition. Hint, hint, hint. Confidence intervals and sampling distributions have the same conditions. All three are the same. This is a different thing, and we can't do it right here because we've sampled way more than 10%. Garrett, great question. Why does it have to be less than 10%? It actually has to deal with the mathematics. There was such a good article, and I cannot find it. It showed the mathematics and how the mathematics break down if you sample too much. So, Garrett, it's a really great question. It can be shown mathematically that the intervals have too much error in them if you sample more than 10% of the population, which is counterintuitive because you'd be like, more is better. But apparently the mathematics just have error in them. Such a great question. I had a really great article, and I swear students would fall asleep when I showed it, but it would answer the question, and I'm not good enough at mathematics to do it, like to show it. Let's do the success failure here. Let's do 2 questions. We want to estimate the true proportion of UT students who walk to campus. We take a sample of 200 students and 30 of them walk to campus. We know that, UT students have flown a plane. Sure, why not? Draw the sampling distribution for the sample proportion for sample size 50. Okay. So let's look at this right here. And what conditions do we meet or not meet? And, or can anyone explain, like, we're random. Well, okay, wait. So we randomly sample for a random sample size. Take a random. Oh, we did some earlier. K right there, Kivian. We did some assignment. Well, assignment 7. Email me because we'll be ending here soon. I got to answer emails because of the test coming up. So which one passes? Which one passes? Which one passes right here and which one fails? So both of these have the success failure condition because they're both proportions, which are both categorical variables. So the first one right here, question 1, and they both have the same third condition. So question 1, does question 1 pass or fail? And can you show me the mathematics? Question 1 passes. And with question 1 passing, we want to check here NP greater than or equal to 10. Oh, no, excuse me. This is NP hat. It's the same condition. It's still success failure. And we want to look at NQ hat greater than or equal to 10 also. So who can tell me what we have here to check this? So both of these have to be greater than or equal to 10. And we have right here N for the sample size. And that's X, which is actually super helpful. That's X. That's N. And NP hat is actually equal to X, but we could solve it. That 200 times, wings up, X over N equals P hat. P hat is equal to 30 over 200, which is equal to 0.15. That's the sample proportion. So the sample proportion right here is that. And we can resolve. We'll just be solving for X. And that is equal to 30. And that means Q hat, the first one does pass. That is correct. And then Q hat is going to be the other side of this. And Q hat is going to equal up to what? It's the students who do not walk to campus in our sample. So that is NQ hat right there. Now for the second one, does it pass or fail? In the second one, we need to do NP. It's the same thing, but it's just we use different notation. NP, NQ greater than or equal to 10 because we're doing the sampling distribution. It's still success failure condition. Important thing to note. Still the same condition. And now what do we have when we solve for this one? We're going to go right here and solve it. And when we solve this, we need to mark what N and P are. So here's N and here's P. And so this is P, which makes Q equal to 0.88. It's just the other side of it. P is equal to 0.12. They're always complements. And so when we do NP right here, we do 50, and we're going to do times 0.12, and all of a sudden we see the issue. That is 6. And 50 times 0.88, and that is going to be 44. So specifically, this one does not meet it. It fails. Bingo. And this is the same condition right here. Yeah, exactly. Sample size change. Yep. It's two completely different questions. And so the top one passes. You need them both to be greater than or equal to 10. And if one of them's good and the other one's bad, that's bad. Whew. Good stuff. Good officers. Is everyone feeling a little bit more on track? How are people feeling? Understanding the success failure condition here. We need at least 10 successes, at least 10 failures, denoted by NP hat or NQ hat greater than or equal to 10 for confidence intervals. This one up top here, let's put it in some nice. We haven't used gold pen in a while. Gold pen, you're back. This is confidence intervals up here, and this one right here is sampling distributions. So sampling distributions. So way better. That's glad to hear. Just remember, you got this. Stay positive. With that, let's head to space. Just talk for a moment. Head out. Whew. How picky will the exam be on decimal places? I don't think too picky. Just make sure to do what it says. I mean, that's picky, right? But if you feel like you got something wrong, just let me know. If you got something wrong that it should have marked right, let me know. Like, hey, Brian, I put 0.184 and it wanted 0.185. I'm like, okay, you got this. Can you please go over how to do number 12? Yeah, let's do that real quick. We said we would. You got it. Let's do it. Okay. We might have part of that up. So I think, let me see. Number 12. Number 12. Gotta find number 12. Yep. Okay. Should be about document number, 40s. It's gonna be around here-ish. There we go. Here we are. We're near it now. I can feel it. Was it earlier? Yeah, it was before class today then. Yes. I think this is it, right? Okay. Part 4 right here? Awesome. So I think it's this one right here, right? So in this one right here, we're looking at... Let me make sure it's the right one. Been here for like 2 hours. Oh, that's awesome. Glad to hear that, Emma. I hope it helps. I hope it helps. It's always about practicing up. I need more Word documents. Part 4, yep. Okay. So when you look at... And we did a different problem here earlier. So when you look at a decision tree, what is the only way R squared can go with a decision tree? When you look at a decision tree, what is the only way R squared can go when we put more splits in the tree? When you put more splits in a tree, R squared can only do this. This is a key concept for this problem. So our R squared in the tree is currently this right here. And how do we know that it's currently that? Let's go look at it. And the R squared is currently right here. There's the R squared right there. So the R squared is only this, and the R squared can only increase. So this automatically knocks out 2 of these. Let's keep the R squared on the screen. So let's do more true. These 2 are gone. So if you look at the R squared, this question says most likely. I'm gonna have to go here in a second. I gotta go answer emails. I'm so sorry. If you look at where it's currently at, usually you don't get big jumps in the R squared. So if it's currently at 0.099, which we can see via the split history, the split history shows us the history of the R squared. You can look over at the side of it. It says R squared right here. So since the R squared is shown in the split history at 0.099, if we were to split again, it can't go down. Do you think it would jump up and go like whee, up here all of a sudden? That's highly unlikely. It might even be impossible by the way the tree is structured right now. There are impossible things to happen that would get into like Gini coefficient and stuff like that for misclassifications in the tree. But don't worry, I'm not going that in depth. Just when you think about this, which of these seems most likely now for this? That it would jump up to 50%, or it would go up a little bit, or it would jump to 50.5, or it would super jump. That last one right there says it's going to go like, whee, it's going to super jump up. It's going to go way, way higher. So if we were to look at right here, the R squared would go up to something like this with the next split when it goes to 4 splits. Yeah, it would actually even have to go higher. It'd go to about there. So what do you think is most likely when it does another split? Yep. And does that make sense right there? Great answers. And just kind of understanding, looking at the output, you're probably going to see, like a minimum increase to R squared. You're going to see something along the lines of what we've been seeing in the past. These down here are not like impossible, but they're just kind of unlikely. Some of them might, probably the 0.991 is literally impossible. You're welcome. Exactly, conceptually. Great answer right there. Yep, conceptually. Let's do one more true false to end. You ready? What true false should the chapter be from? All right, one more true false to end. What true false should the chapter be from? What true false do you want me to make a chapter from? A chapter question from? Can you quickly go over the environmental agency? Is it loading? I'll try to do that real quick. Is it loading? I'm going to see if my Pearson's loading. If my Pearson's loading, we could probably try that. And these are all being extended. So the good news on my Pearson is they're all being extended till Sunday. This should be confidence intervals. Is it loading? Okay, it is loading. Really? My Pearson's going to suddenly start working now? Hey, we're still extending it, though. I said it. We're doing it. I'm glad it's working today, though. That's a good thing, but, I mean, I don't like that it didn't work for quite a while. Let's see. Here we go. Ah, this one. Yes, yes, yes. Okay. An environmental agency. Let's take a look right here. Take it from the exam. Oh, you're welcome, Madison. So for this question right here, let's grab it and let's take it. Let's open another Word document. You got this. Look at all the craziness right there. Okay. And let's go to a Word document. Okay. So an environmental agency worries that many cars may be violating the clean emission standards, yada, yada, yada. Doesn't matter. Just random stuff for the question. What we need to look at here is the numbers. The numbers are all that matters. That's all we care about. So what they're doing at first is they're taking a sample of 40 cars And from that sample of 40 cars, they find that 6 of those cars had problems. So this is going to be a sample proportion right here. X over n equals p hat. So they're getting a sample proportion of 15%. And that is found via 6 over 40. So we got 15%. Now, instantaneously, when you find p hat, you want to find q hat, and that would be the complement of their sample proportion. 2% is going to be the margin of error they're looking for, and the 99% is going to be relative to the z-score. So with the z-score right here, we need to go to the David M. Lane applet and get the answer for what the z-score is. It's going to be 2.5758. Not that I know that. It's called Brian Stone. One too many of these. No, I don't know. One time I sat down, and let me put this in the chat here for everybody. One time I sat down and was like, I'm going to memorize as many z-scores as I can. Oh, Cody, rewind just a moment. We just did that one a moment ago, Cody. Check it out. We can come back to it here, and we'll probably end here in a moment. But we did that one a moment ago. Check it out. Probably about 5-6 minutes in the past. In the past. So here is the z-score. If you notice, the z-score gets even bigger as we get less and less, or more and more confident. The z-score is going to get even bigger from an 80% confident to 90, and you can see the curve covering more areas, which means it's less precise, but it's going to get wider and wider and wider when we go up in confidence. We don't want a 98, we want a 99 right there. So that's the z-score we're going to be using for this problem, and you need to use the David M. Lane, which you won't have to use on the test. We will give you these numbers on the test. So now we need to solve for the sample size. It's wondering, what is the sample size? And let's go ahead and write the interval p hat plus or minus z p hat q hat over n square root. And what you'll notice here is we don't need this part of it. We're only doing the margin of error. So we know that the margin of error is all we're trying to solve for, and we're trying to solve for this right here. So we're can use a standard normal distribution. You can use those tables. Perfectly fine to use them X, but I don't like them. It's just that I actually have the distributions on my phone. I should still have it on here. Oh, did I take it off? No, I got it on here still. So, ran out of space, so I have to re-download it. People have always said to me, like, what if you have to like use these numbers? Wouldn't it be best to have a table? You can see here on my phone, I think you can see it, that I actually have the distribution. You can see the normal curve. I have to like turn the phone sideways, but you can see the normal curve on the phone right there. So I can actually find the numbers via the applet on my phone. So does it actually change? It doesn't orient. So people are often like, well, you can carry the table with you. And I'm like, I can carry my phone with me, and it has all the numbers from the applet. So that is the probabilities distribution applet from Matt Bogner from University of Iowa. Great applet. And so that's why I like using the applets, because you can get like really exact answers. So now let's take a look right here. We're solving for n. Do we have all the information? We do. So we're going to go right here and put in p hat times q hat square root over n, z-score of 2.5758. And then we're going to do the margin of error. The margin of error is 2%. All of this up here comes from the answers up above. If you've noticed what we circled the margin of error, which is 2%. The z-score was found via the David M. Lane applet. So you have to go to the applet and find the z-score relative to 99% shaded in the middle, just in case you need the numbers. Here's 80%. There's 90%, 95, 1.96 classic, 98, and 99% right there. So I think I went 98% too quickly. There's 98. Pause the screen if you need it. And so those are all the z-scores relative to the percent confidence. And now we can actually just solve from here if we like. Let's go ahead and divide 0.02 divided by 2.5758, and we get that right there. So I'm just going to write 0.077 right here. Just as a placeholder, I would carry all my decimals. So now I'm going to square this to take off the square root on this. So let's square that. Oh, I don't like the way that looks. Let's do it the better way. It's better if you carry out the notation. So what I'm going to do is I'm going to use the notation, and I'm going to solve it mathematically for the answer, because the decimals are really going to run amok. They're going to not be good. So we're going to divide by the z-score like we just did. and then we're going to square it like we just did. And then we're going to get the following p hat times q hat over n. Then we're going to flip it. So it's like pop it, twist it, flip it. Because we have right here that if you just flip it, it'll be the same thing, but then n will be on top. And that's where we want it because we want to solve for that. So now we're just flipping everything, which you can mathematically do. That's a rule of mathematics that you can flip stuff. And it's the same if you flip both sides. It's still mathematically equal. And now you can see we just need to multiply both sides by this because we're just going to multiply the bottom right here to get what n is equal to. And then we can plug back in the numbers and solve. So we're just doing algebra right here, fun algebra problem. But now that we've algebraed this, we can much easier plug in our numbers. So the numbers we're going to plug in right here, I'll put it solved up here, is going to be 0.15 times 0.85. And then we're taking the 2.5758. Then we're dividing that by 0.02, margin of error, and we're squaring that. Do not forget to square it, and this will solve for for n. I don't know what we're solving for. So we're going to take right here the 2.5758. All the decimals, every one of them. 2.5758 divided by 0.02. Square that. Good. Everything seems right. Times that by 0.85. Times that by 0.15. And then usually these have you round up. And I think we've done it properly. That looks about right. It's going to have us round up. So no matter what you get, you must round up. You must. So round up to the nearest whole number. Doesn't matter if this is a 1 or anything. Did we do it? Yes. End today on a high note. And I think, does it have enough of a margin of error where it would have given us it had we... Ah, good. It's got a little bit of a give on the problem. Oh, wow. That's a lot of a give. Okay, good. It doesn't have that much more of a give. It's got a little bit of a plus or minus, which is nice. So if you do not carry all your decimals out, it looks to be centered at about this plus or minus 2. So it's that answer plus or minus 2, it looks like. Because if we go down to 2, it's going to say we're wrong. And if we go outside of 8 right here, it's going to say we're right. You're welcome, Courtney. Great question right there. This basically helps solve the problem right here. Let's go to that last Word document. Let's just wait right here. Let's put a little music on while we go through the Word documents. All the Word documents. There we go. Almost 60 Word documents. And so this equation right here, the sample proportion times the complement of the sample proportion times the z-score over the margin of error squared is going to give you the following, which will solve for the sample size. Let's head back to the screen. One last true-false stand though. True or false? Yeah, I should look. Let me compose a true or false that's relative to the test. Oh, good. I spell true. Okay. I've already said that today. I mean, I didn't directly say it. I'm trying to find one that I haven't mentioned. See, some of them are just so false that I don't want to say it. It's like, and I can't even come up with a different one. Mention that. Oh. Okay, good. I like this. Okay. Here we go. True or false? True or false? Good. This is not the exact same question, but it works off of it. Okay, here we go. True or false? True or false? The only way to change the margin of error in an interval is to change the confidence level. The only way to change the margin of error in an interval is to change the confidence level. True or false? Let's look at the interval itself. We're here in space. Just listening to some music. Oh, that's the end of our music? That's a bummer. Very what? Very false. Very false. Exactly, Parker. Great job right there. Now, This is not directly on the test, at least from what I saw, but I mean, the same concept. But if you change if you make it more confident, making it more confident will make it wider. Like that's the z-score. The z-score controls the width of the interval. So the z-score is literally going to control the percent confidence. So the z-score will make it wider, but also sample size, increasing sample size. So more confident equals less precise. But larger sample size equals more precise. If you just look at this mathematically, so thinking about this the way it looks, when you look at the sample size right here, if you increase the sample size, that'll decrease the margin of error, i.e. more precise. But if you get more confident, the z-score goes up and the interval gets wider because you're multiplying by z. So I hope kind of viewing these things visually here like this kind of makes sense. Have you reviewed the water heater question on the practice test? Good. I'm going to head off here, Hope, I'm so sorry. Everybody, thank you so much. Let me do this. I'm going to drop this in the chat right now. We did do the water heater question earlier today during office hours. So we did it today. I'm going to head off to answer emails because I'm worried because if I don't answer emails, then people might be like, hey, bro, my test isn't loading or like something happened. So let me put this in the chat right here. There are on the Stats 1 review page, if you're watching right now, there are on the Stats 1 review page playlists of all the questions, and I'm going to put in here. Is this the always hot water heater questions? Let me show this. So head over to the main screen. And thank you so much, everyone, for showing up. Hashtag show up. We know what's going on right here. Hashtag show up. So this is the additional charges one, and sampling methods. Wait, what? Phat 6 review exam. Reload the page right here. So I think it's question number 6. So here it is right here. Sampling distribution of the sample portion. So here it is right here. Let's copy video at current time. And there we go. Got him. Someone said something. So question 6. And we did it earlier today. So if you want to see another version of it, I don't know what that means, Tyler. But great questions, everybody. I'm going to head off. Please email me if you have questions. I looked and I had like 40 or 50 emails last time I looked, but great work. We got this. Show up next class. Make it happen. Good luck tonight. You're welcome, Hope. Keep up the great work. Let's head over here. Let's play some Celeste music. No, we need like happy music. We're going to end with my favorite song. Here we go. Everybody, you got this. Good luck tonight. I will see you later. Bye for now, everyone. Bye. It's Josiah Wilkinson, best pianist ever.